Okay, welcome back. If you watched the last video, that's probably as good of a cliffhanger as we get in PChem. I asked this question. We were looking at a pressure composition diagram of some binary mixture. Liquids were up here, gases were down here. These were the phase boundaries that separated them. The question is, what exists in this region? And here's the answer. In this region, we have both liquids and gases. When we have a pure substance, we have lines where two phases coexist. But when we have mixtures of things, there are now areas where two phases can coexist. And this is a pretty subtle, nuanced thing to understand, right? And what I want to talk about in this video. But I tried to express the essential idea to you right here. These boundaries defined the compositions of the system. And so if I'm at some area in the two region boundary, I cannot necessarily have a liquid or a gas that exists at a particular composition. I can never go outside of the region bound by these boundaries. But what you can get is a system where one phase is enriched in A, the other phase is enriched in B, and what you do is mix and match these things so that you get the right overall composition of the system. So I should really put on here when two phases are present. When two phases are present, there are two questions what we can ask. The first is, what are the compositions of the liquid and gas phases at some point? And the second is, what are the relative amounts of liquid and gas phases at some point in this region? These are two separate and independent questions, right? So I want to talk about how you answer them in this video. I'm going to move my talking head here to the bottom if I can. We'll see how this works. The first question, what are the phases? Sorry, what are the compositions that are present at some point in the phase diagram? Here's how you do it. To determine compositions, you draw a horizontal line to the liquid and gas boundaries. So I tried to zoom in on some region here. Imagine I was interested at some point in the two-phase region right here. And I asked, what are the composition of the liquid and gas phases when the system is overall at this composition? So what you start by doing is drawing a horizontal line which connects the liquid and gas phases. The horizontal line is called a tie line. You then drop vertical lines down to the axes and read off. So in this particular problem, if I was interested at this point, right, in the gas phase, I might have a system that is 0.79 A. I know this is the gas phase because this is the gas phase boundary. I drop down and I get 0.79. Similarly, if I go this way and I read down, I might be 0.26 A in the liquid. So 26% of the moles of the liquid phase are A. Let me ask you some questions. Why don't these values add up to 1? Well, they don't have to, right? What has to add up to 1 is the total amount of A and B in a liquid phase. There's nothing that says the amount of A in the liquid and the amount of A in the gas have to add up into 1. So they don't have to, they're independent quantities. If I know that there is 0.79 A in the gas phase, I can reason that there's 0.21 of B in the gas phase. But again, that's unrelated to the amount that's in the liquid phase. Second question. Does the fact that there is a higher mole fraction of A in the gas phase compared to the liquid phase make sense? The fact that this is bigger than the liquid phase, does that make sense? And I would argue yes, right? If this is the mole fraction of A, I can see that the vapor pressure of pure A, this spot here, is greater than the vapor pressure of pure B. A is more volatile. And if A is more volatile, I would expect the gas to be enriched in the more volatile component. So this all makes sense. That was question 1. The second question is, what are the relative amounts of stuff that are present? And in order to do this, you use what's called the lever rule. Again, you look at your tie line, and what you do is compare the length of the line connecting your point of interest to the gas phase compared to the length from your point of interest to the liquid phase. And the lever rule is written here. Number of molecules in the gas phase times this length will be equal to the number of molecules in the liquid phase times this length. And what I would tell you is that this is like the fulcrum point of a teeter-totter. Imagine here's a teeter-totter with the fulcrum right there. Where does the heavier mass have to sit? Well, if this is mass 2, right, the heavy thing has to sit up here. Right? M1, L1 equals M2, L2. Heavy thing has to be here. Right? Similarly, if this is the fulcrum point of my tie line, I'm going to have more molecules of gas over here. So if I were comparing these lengths, I'm qualitatively estimating this, but I said that this length in the gas phase is twice the length in the liquid phase. Length in the gas phase is twice the length in the liquid phase. And if that is true, you can do some substitutions and show that the number in the liquid phase is twice as big as the number in the gas phase. I got more stuff here, just like the heavy object is at this point in the fulcrum. All right, this was a short one. I'm going to stop here and talk about temperature composition diagrams next time, and I will see you then. Last topic.